Okay, folks, we are back, and we have some background music again here at the church. So again, if you like the organ music, there you go. If you don't, I think we're okay. So this is the second video for week 5. I think I did that first one a little bit fast, but hopefully you got the point there. So we're still on the slides for the week, and we are looking at buffers. So if you want to write down all the definitions there, I have an example on the slides which I'm going to go through. So a buffer, I'm not going to write all that down, it's on the slide. So a buffer is a solution that resists changes in pH. Fine, that's the generic definition of a buffer. But what does that mean? Well, what that means is when you have a buffer, that means you have a high concentration of a weak acid, like acetic acid, and its conjugate base, acetate ions, and those two things are present in fairly high concentrations. And what that does is that sets up an equilibrium where this equilibrium can shift back and forth and hold this H plus fairly constant. It's not perfect, but buffering systems can do that. So some things we're going to do in class. In lab, you're going to learn how to prepare a buffer. I'm not going to worry about that right here. So if you're going to prepare a buffer in the lab, you would physically go grab a bottle of acetic acid, because it's a liquid, so it'd be a bottle, and then a jar of some ionic compound that has acetate, like sodium acetate. Because the sodium, as you know, doesn't have any acid-base properties, but acetate does. So you would get solid sodium acetate, some acetic acid, and mix them together. So acid over here, base over here, dump them together, and then you would have a buffer system. So I'm kind of skipping all that preparation stuff because you're going to see that in the 126 lab, or if you're a chemistry major, you'll see that with Dr. Richardson. So we're just going to cut to the chase here. Okay, so this is example, and I think I'm calling this example number 1. Oh, the last thing there, the Henderson-Hasselbalch equation, just hold off on that one now. You can write it down. So this is just the example we're looking at here. So how does that work? Well, this is all the Chatelier's principle. I'll just kind of keep it to the example that's here. Well, okay, that's the idea. Again, a buffer maintains pH. So what happens if we add acid to that equilibrium? Okay. Well, you know this already. If I add hydrochloric acid, the chloride does not have acid-base properties. All we're doing is dumping in a bunch of excess H+. Well, what does Le Chatelier's principle tell us? Le Chatelier's principle tells us if I add a bunch of H+, we're going to get a shift left. It's Le Chatelier. We just dump a bunch in there, and the reaction is going to shift this way to reduce it back down to where it started. Well, sure, it's going to reduce this along the way, and it's going to increase this along the way. That's the point. That's the whole point. It brings the H plus down, but it has to bring this one down or this one up simultaneously. But that's the point. The point is to bring the H plus back to where it started. That is simple Le Chatelier's principle. Well, what if I add something like a strong base? Like OH minus. Well, this is kind of maybe going back a little ways, but if you dump a bunch of OH minus in there, well, what's it going to do? Well, that's base. It's going to react with the acid, and that's called a neutralization reactant. OH minus and H plus, well, those produce water. Strong base, strong acid here. So those combine to make water. So that effectively reduces the H plus concentration, pulls it out. So we're going to get a shift right to restore the H plus to its original amount, because you're pulling it out and the equilibrium will shift to the right. Yes, you'll lose some acetic acid, you'll gain some acetate, but the point is to hold this constant. That's really how it works. Okay, I think that's probably all we need to know there. So it shifts back and forth. If you add acid, it shifts left. If you add base, it shifts right. Okay, that should be pretty straightforward. That's A and B. Now the one here is a calculation. So this is letter C. Actually, you're going to find this calculation really easy. I can probably fit it in right here. A, B, C. What does it say? Calculate the pH. And we're taking 10th molar. So this is stuff we're going to do in the lab. You could go to the lab and make a 10th molar solution of this, 0.10 molar, and a 0.10 molar solution of this. That's solution prep. So it's 2 solution preps, and you dump them together. Again, we're not doing that in class. We're just going to assume you know how to make solutions. And what's the pH? And then what happens to the pH if we change something? Okay. This is probably going to end up being one of the shortest videos out there. So what is the pH of that solution? And they're both 0.10 molar. Okay, so this is a slight variation of an ice calculation. So I'm going to bring down, so we want to find the H plus. So yeah, it's kind of a weird ice calculation, but it's still an ice calculation. So we've got the acetic acid, H2, HC2, H3, O2. Oh, this is monoprotic, by the way. I think some of you in lab have seen this written a little differently. So it's monoprotic, but not that it matters because you're told that here, in effect. So we've got this equilibrium. Okay, so that's the equilibrium, and we're going to do an ice calculation. We're probably getting tired of these. And the initial concentration of acetic acid is 0.10, and normally we write zeros and zeros, don't we? We just go blah, blah, 0, 0. Nah, that's not the case here. You make this solution to be 0.10, you make this solution to be 0.10, and you dump them together. So you have to have an initial concentration here and here. And this seems kind of odd, but we're going to assume that this is 0 to start out with, because it's like a freeze frame again. It's a hypothetical situation. So what this equilibrium has to do is this equilibrium, well, it has to shift that way somewhat to give some H plus. You can't have negative H plus. So that has to be a positive X. It has to go up because it's at 0. Well, if that goes up, that has to go up. And if those go up, that has to go down. Fine. So 0.10 minus X, X, 0.10 plus X. Okay, by the way, this is an acid equilibrium. So we would look up a Ka for this. You can have the exact opposite, by the way. You can have a base and its conjugate acid as a buffer. So we would have a Kb. It should be pretty straightforward. And you can look up the Ka for acetic acid. We've used that a gazillion times this semester. So we're going to set up, well, we just set it up and solve for X. So we're going to apply the 5% rule here and here. If it applies to that 0.1, why wouldn't it apply to that 0.1? It has to. It's just, we haven't seen a problem exactly like this before, but it's the same basic idea. So here we have Ka, which is 1.8 times 10 to the minus 5. We've used that before, you can look that one up. Is going to be equal to X times the quantity, 0.10 plus X, over 0.10 minus X. Normally we put like an X squared there, but we're not going to do that in this case. So yeah, that's the key. We have an X in the numerator now that we can't just ignore. So I made this problem maybe a little bit too easy. So we're going to assume the 5% rule is there and there. Well, that seems kind of strange, doesn't it? Because if I do that, and I made this problem kind of easy because these two concentrations I made exactly the same. That's not always the case, by the way. I could have made this 0.5 and made this 0.01. Just keep that in mind. So we're going to assume both of those are negligible compared to 0.1. You can double check that. Well, actually, it's very easy to do. So you end up getting 0.1, well, okay. This ends up being really easy. X ends up being 1.8 times 10 to the minus 5 molar. Numerically, it's the exact same value as the Ka. The 0.1s just cancel, numerator and denominator. And the 5% rule checks. Check it yourself, always check that. And X is the H plus, like it often is, and you end up getting a pH of 4.74. Okay, makes sense. It's a weak acid, so it's weakly acidic, so the pH of this buffer system would be 4.74. No problem. Let's do another one though, to make sure. What does part D ask you? Part D says, calculate the pH if the initial acetate concentration is doubled. So we're going to repeat this calculation if this is doubled. So I'm going to erase most of this and do part D right here, because I don't want to have to erase all of that. So stop the video and write this down if you want to. So this is going to be D, and I'm going to leave this the same. What did it say? Double? If the acetate concentration is double. So we're just doubling that. It still has to be plus. We're doubling that. And I guess I'll rewrite this because it looks messy. Oh, by the way, we can make a hypothesis here. Would the pH of this solution be greater than, less than, or equal to this? Well, okay, we just doubled the C2H3O2. So, that is the conjugate base of acetic acid. That's acetic acid, this is acetate, it's an acid-base pair. I just added more of the basic component. So the solution should become more basic. So I'm predicting this pH should actually go up. It should, because we have more of the conjugate base than we do the acid. But let's just solve it. I mean, you can probably see where this is going. So we're going to have 1.8 times 10 to the minus 5 is approximately, I'm going to skip the whole plus x minus x thing. Well, now I'll set it up. It's going to be x times 0.20 plus x. 0.10 minus x. Again, we're assuming that's 0, and that's 0. Negligible, not really 0. So the only thing that the math changes here is that we have 1.5 and 0.2, so those don't cancel anymore. So you've actually got to solve for x here. And I'll let you do that. So x, and I came up with this, if you solve for x, you get 9.0 times 10 to the minus 6 molar. And that's a pH of 5.05, which is more basic. It's not hugely more basic. It's not totally basic. It's not above 7, but it is a higher pH than the original one, 4.74, which we would expect because this is a more basic component. Excuse me. And that's basically what we're going to do with buffers here. I don't think there's anything more. Also, there's one more thing. The last part. Just because you're going to do this in lab more, calculate the pH, and this is number 3. So sorry, I'm a little off with the slides today. Is the Henderson-Hasselbalch equation. It's not a particularly difficult equation, and you'll do more with this in lab. I guess I'm just showing it to you here, just so you know where it comes from, because we hate to give you just math with no explanation whenever possible. So this is number 4, the Henderson-Hasselbalch equation. Yeah. Oh, that's right. I have an example here. So what we're going to do here is, rather than consider a specific acid and a specific base, we're going to do it generically. Let's consider a generic acid, monoprotic. So this is a weak W acid, and this is its conjugate base. So that would be the acetic acid, that would be the acetate, and that's obviously the H plus. So we derive this equation, it's just using some logarithm math. So Ka is H plus times A minus all over HA. Then what we're going to do is take the negative logarithm of each side, negative logarithm of Ka. By the way, what would we call that? The negative logarithm of any variable is what? That would be called the pKa. pH, pOH, pKa. I think we did that a while back. And this is going to be, I'm going to streamline this. Whenever you have this H plus times, what we're going to do is pull the H plus out. This is a legit move. Sorry, I kind of missed my parentheses there. I'm just pulling the H plus out. Because what this says, this allows us to do is, well, minus log of Ka, we can call that, to streamline it a bit, that's called the pKa. The minus log of H plus, you already know what that is, that's called the pH. And we don't have anything to call that, but we want to leave that ratio there. So that's fine. Or, if we rearrange it, this tells us how to calculate the pH of a buffered solution. So if you want to know the pH, of a buffer solution, you take the pKa, so you look up the Ka on a table, and take the pKa of it, look that up, and then, let's see, I've got to bring this over here. Add to that the logarithm of the ratio of the conjugate base concentration divided by the acid concentration. So the pH of a buffer solution is the pKa from a table minus the log of the ratio of the concentrations. That's called a Henderson-Hasselbalch equation. You're going to use this in lab to prepare buffers. Okay, I just want to show you this real quick. Well, so how do you use this? If you apply this to the previous problem that we just did, so for part D of that previous problem, we already know the answer is 5.04. This is just another way of doing it. So the pH of that solution in part D would be the pKa, so the minus logarithm of 1.8 times 10 to the minus 5 plus the logarithm of the ratio of the concentrations. So the acetate, the A minus was 0.20 molar, the HA was 0.10 molar, and just do the math. pH equals, and if you do pKa, you come up with 4.74. And if you do that ratio, take the logarithm. Well, you get the same answer. What I like about this is what I like about doing problems using the Henderson-Hasselbalch equation. So the pKa is pretty straightforward. Well, if your conjugate base concentration is greater than your acid concentration, this is a positive number and the pH goes up from the pKa. If I switch these two around, this logarithm would be negative and the pH would go down. So just make sure I think this is a good way to do it. If you put in more conjugate base, the pH goes up. If you put in more acid, that pH is going to go down. So this is a nice equation that kind of illustrates the principles in a fairly straightforward fashion. So that's the Henderson-Hasselbalch equation. It's really just a nice convenient extension off of ice tables, which is all it's really meant to do. And that's where we'll end off for today, unless I'm missing something. Just checking my notes. Yep, oh, I'm sorry, one last thing about buffers. Almost forgot this. You'll do this in lab. Basically, when you want to pick a buffer, I don't think I'm going to put any questions on this on the exam. Well, actually, there's one question on homework. So, pick a buffer. Let's see, how do I want to explain this? I forget how I explained it in the notes. Well, it's there. Oh, yeah. Basically, when you make a buffer, you have some pH in mind. Like you want to buffer the solution at a certain pH. How do you know what buffer system to pick? Well, first off, you find a target pH. This is more of a lab thing. Have a target pH, and then pick. You want to find some pKa, that is plus or minus 1 pH unit away from your target pH. I'm making that kind of clunky here. So the Ka for acetic acid is 4.74. So if you wanted to buffer a system at a pH of 7, you would not choose acetic acid and acetate. So basically you have a target pH and you pick a pKa that's plus or minus 1 unit away from it. This is a guideline. I'm not going to dwell on that one too much. That's more of a lab thing. That's where we'll end this video since I'm kind of babbling.